I'm gonna tell you about certifying derivation of state machines. Many security protocols are implemented via low-level state machines. An example which I focus today is TLS. It's the successor of SSL, a cryptographic protocol for secure network communications like web browsing. So let's briefly see how a regular TLS session looks like. The first step is key exchange. In this step, the client and server decide which cryptographic algorithm to use and establish keys and parameters. And then they can send messages for authentication if they want. This process so far is called handshake. Then finally, we can securely send HTTP requests or something. And usually a server handles multiple sessions concurrently. Typical implementation looks like this. Server receives a message and checks its message type and the current state. Then it performs local computations or sends something back to client and updates the current state. So the code explicitly handles where the program counter is, which we does not do in high-level programming. Also, the server consists of nested state machines. The top-level server communicates with the state machine for reading specified bytes of messages per connection, and that reader state machine communicates with the core TLS state machine. Such hand-written state machines can easily cause bugs. Change Cipher Spec injection is famous. Old versions of OpenSSL accepted a message called change Cipher Spec at an inappropriate stage in the state machine, and that can allow an attacker to decrypt and modify messages. After that vulnerability was revealed, people found that actually many TLS implementations have state machine bugs like allowing unexpected messages. To avoid those bugs, why don't we write high-level code which is easy to read and verify, and then compile it into a state machine? Here is a small example. We have a simple recursive function that equals received messages until it receives an empty string. Then the state machine should look like this. We have a state for each system call, receive and send in this case, and we can realize this diagram as this code. We have a step function. It takes the current state and the result of the previous system call. It returns none if the next state is the final state. Otherwise, it returns the pair of the next state and the system call to run at this point. So we give a Coq library with which we can write high-level code and compile it into a state machine. We implemented TLS with our library. The source language supports coroutines, so then it can handle concurrency between connections. Our compiler automatically proves that the source and target programs are equivalent. Then we convert the target program into Haskell so that we can generate an executable. Our implementation consists of nested coroutines, so then they naturally correspond to the nested state machines we saw earlier. The core per connection handshake is a child coroutine of a coroutine for reading and writing. Here, resume is the keyword for calling a child coroutine. In Python, it's named send or next. And this read-write is a child coroutine of the top-level server. The top-level server repeatedly catches an event which is either accepting a new connection or receiving a message from a client. When accepting a new connection, it spawns a new child and inserts it into a data structure. And when receiving a message from a client, it tries to find a child for the client and resume that child. This code is compiled to the nested state machines and then converted to Haskell. Then we have a working TLS server.